We have a collective blind spot in modern data architecture. If you audit actual workloads today, over 90% of analytical tasks fit comfortably on a single node or a hybrid local cloud setup. Yet the industry spent the last decade building as if every company operated at petabyte scale. We constructed massive distributed systems and heavy Spark clusters to solve problems most organizations simply don't have. This created a severe operational bottleneck. To get clean data out of legacy distributed cloud warehouses, data scientists became dependent on data engineers, waiting hours or days just to run baseline analytics. That friction drove the rise of the Duck Stack. By bringing vectorized, columnar, in-process analytics back to local execution, DuckDB bypasses the distributed cluster entirely. Designing for imaginary scale built an artificial wall between raw data and insights. Moving to a local-first architecture dismantles that wall, finally matching the compute engine to the actual size of the problem. This shift has sparked a bold provocation across the industry, the idea that data science and data engineering are on the verge of completely collapsing into a single unified domain. To be clear, job titles are not disappearing. What is collapsing is the traditional high-latency feedback loop that used to define data engineering. The architectural mechanism driving this change is the transition to a hybrid execution model known as dual execution. Making this model functional at scale requires MotherDuck, a hybrid cloud compute layer built specifically to sit directly on top of DuckDB. By trading heavy distributed dependencies for agile hybrid execution, this stack speeds up traditional analytics while simultaneously creating the exact low-latency compute engine required to power modern AI engineering. Look at how a standard data pipeline used to operate. It starts simply enough, with a developer writing SQL or Python to analyze a batch of raw data. This maps the legacy workflow. The code hits a barrier. Before running tests, developers deploy to staging. Then, the system spins up a compute cluster to process data, introducing severe delays. Finally, waiting for cloud warehouse results creates endless latency loops and runaway costs. DuckDB flips this entire workflow. A single developer can now bypass staging and clusters entirely, querying multi-gigabyte files locally in a matter of milliseconds. It executes directly against columnar formats like Parquet, CSV, and Iceberg, or Duck Lake files, right inside local memory. Taking those heavy multi-node deployment steps and replacing them with instantaneous local memory transforms a severe operational roadblock into a frictionless, zero-cost development sandbox. For a data developer, dual execution means you no longer have to maintain separate logic for your sandbox and your production environment. This side-by-side architecture shows the process. On the left, the local loop rapidly queries files in memory. Once validated, you push the exact same SQL directly to MotherDuck. Light tasks stay local, but heavy analytical workloads automatically route to the cloud, altering no code. MotherDuck handles this offloading by avoiding monolithic server clusters. Instead, it relies on minimal infrastructure powered by per-user isolated compute instances. Because the SQL environment remains perfectly consistent across both local and cloud environments, the traditional boundary between development and production disappears, allowing for radically faster iteration. This low-latency architecture maps perfectly onto the new requirements of AI engineering, where AI agents require rapid, iterative access to structured context. To function effectively, autonomous agents must retrieve specific contextual data at extreme velocities, making thousands of microdecisions per minute. Traditional cloud data warehouses fail under these conditions. Hitting a standard warehouse with thousands of rapid individual agent requests introduces massive query latency and causes compute costs to skyrocket. MotherDuck assigns isolated execution environments, called ducklings, for rapid requests. The Model Context Protocol, or MCP, gives language models a direct pathway to query these ducklings. Through MCP, agents run queries across WASM in the browser, local Python runtimes, or the MotherDuck cloud. This setup allows an LLM to pull exact analytical insights directly from the data source, completely bypassing the heavy, expensive routing of a legacy data warehouse. By delivering hyper-isolated, low-latency compute that scales efficiently for individual requests, MotherDuck provides a structural solution to the AI context bottleneck. This brings us back to the initial provocation from our hook. Why haven't data science and data engineering merged into a single job title? We have to draw a strict line between tooling convergence and the operational realities of maintaining data systems at scale. In this diagram, the left circle is tooling convergence. DuckDB, Polars, and dbt let one person handle ingestion, transformation, and analysis. The right circle is operational scale, data governance, pipeline orchestration, and rigid SLAs. Their intersection forms a new role, the full-stack data developer. We see an identical pattern in AI. MotherDuck acts as the analytical compute engine for AI context, but the broader AI stack, including prompt orchestration, evaluations, fine-tuning, and guardrails, remains a highly distinct engineering discipline. The Duck ecosystem makes building pipelines exponentially easier and more accessible. However, keeping complex production systems resilient still mandates dedicated engineering oversight well beyond just running fast SQL. Zooming out, this architectural schematic illustrates the complete modern data pipeline. Data flows seamlessly from a local laptop node up to a hybrid cloud layer and directly into an AI agent context retrieval system. The Duck ecosystem successfully eliminates unnecessary heavy infrastructure for the medium data workloads that make up the vast majority of real-world analytics. For AI engineering, it provides a highly specialized, low-latency, cost-controlled compute engine driven by hypertenancy. Data scientists are now empowered to handle their own data engineering tasks without waiting on a separate infrastructure team. Meanwhile, data engineers are free to architect resilient pipelines at scale with a fraction of their previous infrastructure overhead. Monolithic, rigid data structures are shattering, replaced by modular, interconnected systems. The question now is how you are approaching this shift. Are you evaluating these tools simply to migrate existing pipelines, or are you reconsidering your broader architectural standpoint? The future of data infrastructure belongs to the full-stack data developer. It belongs to those empowered by local-first, seamlessly scalable compute engines that finally eliminate the absolute burden of cloud overhead.